With that, I will take any questions if anybody has any questions or is even still awake. So.
So that's real applause, because he finished early.
Yes.
Any questions?
Is a question. Is your modification, is it already there in the OpenStack SX distribution?
Sorry, I think I heard your question. Let me make sure. Your question was that, is this code currently available in the S6 release or within the OpenStack main branch, right?
That's right.
Okay. All right. The answer is no. We have our own fork, which we call the DoDCS project. That in and of itself is free and open source. You can go to our GitHub. Actually, I can provide a link, or you can send me an email. So that is all open source. We are currently underway in merging much of these, as well as many other modifications to OpenStack into Folsom. So we right now, our own implementation that we call our stable branch is based on S6. But we are merging a lot of these, hopefully, into Folsom, which the third review is coming up in a week and a half. So I have a lot of work to do on that front. But we hope to have this at least partially within Folsom. So, as well as many other features that we're developing within the DoDCS team, including advanced proximity scheduling, bare metal provisioning through OpenStack, as well as many other modifications to OpenStack that directly support high-performance computing within infrastructure as a service within OpenStack. So, send me an email. I can direct you. I guess I don't have my email here. Sorry. It's just ajyounge@indiana.edu. I can send you a link, and you can look at the latest code. I will say we do have another implementation of this that originally uses the gVertis, which is a front-end API mechanism that I described earlier, along with LXC. This is not a good solution for OpenStack as a whole, because LXC, the only way we control access to GPUs is through a whitelist, which is controllable within the VM. So this is only for specific deployment within a secure, trusted user environment, which for certain deployments we have. However, if you're running a public cloud, that doesn't obviously work, which is where the security features, specifically within Zen and the VTD technologies, matter. So, any other questions?
Somebody must want to ask the last question of the summer school. Otherwise, the prize goes to UCLA.
Can y'all hear us?
Yep.
Okay.
Yeah, so this is a question from LSU, please. So the question is, like, how hard it is to virtualize the GPUs in the operating system level? Like, for example, having the GPUs supporting access to one GPU from more than one process, which in a sense can make the GPUs easier to virtualize for different virtual machines. Maybe like this is a question that should be forwarded to people in like engineering teams in NVIDIA, but do you have any insights about that? Thank you.
So one of the mechanisms, the PCI pass-through mechanism specifically gives one GPU and the entire control of the GPU directly to a specific VM, and provides mechanisms that specifically do not allow other VMs or even the original host or DOM0 to talk to that GPU, even if it wanted to. It doesn't even, when you pass it directly to a VM, the host doesn't even know it exists anymore. So, and that is really what we find users really want. They want to grab these GPUs all for themselves. And we can, of course, assign multiple GPUs to a single VM instance. Right now we're concentrating predominantly just on one GPU to one VM. But there's no inherent limitation in that design. You could do multiple GPUs to a single VM. The interesting idea comes when we would like to use live migration, where, for instance, we're doing a lot of CPU-intensive computation, and we get to a point where we want to start our GPU computation. Instead of calling a remote API, for instance, with what our CUDA utilizes, we could migrate the entire machine to a host that has GPUs and connect to that GPU. Now that functionality isn't quite there yet with Zen, and it is currently under development, but will take some time. So that's a long-term goal. But right now, using the VTD or IOMMU and giving specific a one-to-one relationship or a two-to-one relationship of VMs to GPUs seems to work well. So, does that answer your question, or did I not understand it correctly?
Okay, can you hear me now?
Yeah.
Yeah, okay, so my question was like basically more related to having like using the GPU from more than one place rather than associating 2 GPUs to one virtual machine. But I think you answered it the other way around, whether you can have like 2 GPUs associated to one virtual machine.
I see. So you want multiple VMs to share a single GPU. Is that your question? Is that possible?
Yeah, that's what I had in mind.
You can push the
Okay. So with that, there's where the front-end APIs are better fit for that. So you could have multiple VM instances, each with, let me rewind here to this slide, if you guys can still see that. The idea here this model fits that request best, in that you could have multiple client-side applications hosted within a VM that has the Arcuda library that, let's say you have 2 of those and they both make the remote method invocation to the Arcuda daemon to thereby share computation within a CUDA device. Now this is possible. They're, I think, implementing queuing mechanisms, so it's not actually doing simultaneous computation. You actually have to wait for one request to be processed and then sent out, and then you can take in a new request. So it's not like 2 GPU applications are actually running on the GPU at the same time. I don't think that's really supported within the way NVIDIA has designed the CUDA architecture, but that would be an interesting setup. I've yet to see that from NVIDIA, though. So if you're looking for multiple VMs to share a CUDA device, this is definitely the way to go. From what we've seen from our application developers, they want the opposite. They want to grab as many VMs or as many GPUs as possible within a given VM. So, all right, thanks. Any other questions?